अरे क्या पापा भेजे किसके बगल में रूम
रिकॉर्डिंग चल रहा है। Hello everyone. So welcome to the class. So basically this is the 11th week and we all know we are coming to the end. So one more class will be there and other class will be there for basically solving some of the doubts. So I'm requesting if any doubts are there, please do mail me. So 25, I want to have 13 weeks, so 12 weeks for these things and 1 week for your questions and answers. So how many of you watched all the 11-week lectures? I just want to know some of the updates. Okay, Lakshmi, nice. Ananta, nice. Okay, so you both are giving exam, right? You both will be giving exam.
Yes,
Nice.
yes.
Okay, okay, okay. That's great. Yeah, nice. So, Lakanya, I think you are very new to my class. I don't know. Otherwise, I know both of them. Let me put charger.
Yes, madam. I not joined in previous classes, but I watched offline YouTube uploaded videos.
Okay, that's great. Okay. You watched all the
Yes,
class 11 weeks also, right?
yes, madam. Yes, madam.
That's nice. Okay. So yeah, this week was basically based on some of the application, and this week is little not that much tricky. But what I feel, I was going through the content. So the SVD thing is the most important. This singular value decomposition and also sensitivity and analysis, because two, three questions will definitely come from sensitivity and analysis. Other thing is SVD, how you can do everything using SVD. And what is the application of SVD and eigenvalue eigenvector decomposition. So if you understand both things, and the least square solution, least norm solution, and so yeah, in the last week we will go through some of the like formula revising class like that. So that you people also have some of the revision sort of thing. So in this week, if you see, so graph or a network, a structure or something, the structure that is used to represent the relationship among the objects is can be represented as a graph. So this is very important for a AI/ML perspective. So what we have observed, I was also thinking as we move forward, we'll see some of the more relation with the AI. But what we have observed in this course is like most of the things are linear algebra itself, but somewhere in between only we saw how it can be used for AI and its application. So if you see, so all the things are linear algebra only. So the structure or the graph or a network is useful for recommendation analysis or analysis of a web search or something like that. Because in Google also, if you see chat GPT analysis, so how it is based on, so it is based on LLM model. So LLM model basically one prediction is based on all the five or six features. So this features is itself related to some the other features through a graph or through a network. So how they are related, by what weight they are related, that is represented by the weight. Okay, so if you see the social network, so this is undirected graph, there is no direction, and if direction is there, then it is a directed graph, that is a web graph. Okay, so this edges can be directed or undirected. So the graph can be represented by V or E. So is showing this is vertices and E is edges. So suppose you have six vertices, so 1, 2, 3, 4, 5, 6, and edges is like 1 to 2, 3 to 4, 4 to 5, like this. So undirected graph, definitely this, when this is undirected, then it will not have any direction. Ij is equals to ji. So directed will not be having the same interpretation. So this, yeah, weights is very important, because that weight is reflecting how important that particular feature is, or how much it is related to the previous feature. Okay, so that is given by the weight. So yeah, so if you represent the walk, so walk is a sequence of the suppose vertices j1, j2 to jk, so that for jr to jr plus 1 there is an edges. Okay, that is suppose 1, 2, 2, 3 or 4, 5, if it is not present, so no restriction on repetition of the vertices. Suppose it is because walk is there, you can't repeat, but anyway you can repeat, but it will not have any restriction. Okay, suppose path is also a sequence of the vertices j1, j2, jk, so that for all jr to jr plus 1 there is an edges, and again there is no repetition on the vertices. So if you see this 1, 2, 3, 2, so again it is repeating, so it is not following a path. So it was not a path, but it is 1, 2, 3, 4, it is a path. So cycle is a path. So j1, j2 to gk with J1 is equals to Jk. Obviously, it is coming back to the previous one from where it is starting. So if you see the connected graph, yeah, so connected graph, it is actually an undirected graph. So which is if there exists a path between each pair of the vertices. So connected means connected from everything. For example, if you see the hexagon itself, so if you join all the vertices inside also hexagon, so it will be connected graph. Okay, we will see here, for example. So undirected graph which is not connected can be divided into a number of connected components. Yeah, here if two things are there, it can be divided into two things. So not true in case of directed graph. So that is not true in case of directed graph. So these are some definitions you can just see. So a directed graph is strongly connected if the directed paths exist between each pair of the vertices in either direction. That is, so what it is saying, the directed graph is actually, it will be connected if the directed paths exist between each pair of the vertices, her direction, in every direction. So if you see some of the distance, so here these are some examples: path, walk. So distance is also one of the examples. Here the number of edges present in the shortest path from I to j is called distance. Yeah, yeah. So every time whenever we call the distance, so distance is if 2 points is not there, so you have to assume it by default it has 0 0. For example, 2, this is 4 3 4. So what is the distance is compared? So you have to see what it is. So you have to find from here 0 0. So this is shortest. Suppose this is also, so this will be the shortest. For a network, you have to find the shortest one. Shortest is important. So diameter. So here diameter is the largest distance between any two vertices. So you remember these terminologies will be very important for in the future. So yeah, if you see the graph adjacency matrix, so a directed graph with n vertices and m edges, a square matrix, suppose A, of size n cross n, is called adjacency matrix when Aij, the ijth entry is the weight of the edge from I to j. So this matrix also follows some of the special properties that we will see later. So yeah, but from any graph you should be able to find it. Okay, so this is defined for a directed graph with n matrices and m edges. So what will be the uh, uh, size of this matrices? N cross n, n cross n. Okay, so 1 2 3 4 5, 1 2 3 4 5. So here, because anyway you have to find from every row to every column. So if one is there from one, it is 0 definitely, but otherwise self loop can also be there. Okay, so you have to see this link as a Markov chain that we will see later. But yeah, Markov chain is also one of the important property. So 1 1 is 0. Sometimes it exists, so some weight is there, then that weight will be reflected here in this matrix. So 1 to 2, 1 to 2 is 1. Then 2 to 2 is definitely 0. But yeah, if 2 to 5, suppose 2 to 5, it is 2. Okay. So if you normalize it means you have to divide by the modulus of it, means this norm of every vector. So sometimes we often get confused, like whether we have to normalize with respect to row or with respect to column. So here in the adjacency matrix, we always normalize with respect to row. So you remember this. So if we are normalizing with respect to row, so divide by 5 5 5 like this. Okay, so how will you divide by 5 here? So you have to multiply by 5 here. Okay, then only you can divide by 5. So that you can do. So for undirected graph, so this is for directed graph, you are defining this adjacency matrix. But what for undirected graph? So for undirected graph, we can construct a symmetric graph adjacency matrix. Here the symmetric is not there. Okay, so symmetricity is there in undirected graph. Okay, so in case of unweighted graphs, the entries in the graph adjacency matrix are either 0 or 1. Okay, so powers of the adjacency matrix. So these are some of the properties. So these properties you have to remember, because from these properties there will be a question. So suppose A is a binary adjacency matrix with binary means either the entries is 0 or 1. So A power k, so ij power jth entry of the A power k is equal to the number of walks from the vertex I to vertex j of length exactly k. So yeah, so what does this mean is, so if you find this power of suppose 100, okay, so sometimes we are not able to find this power, and that's why we did LU decomposition, QR decomposition, and the SVD, so that we will be able to find the inverse of a matrix or power of a matrix. Or if you remember, we also characterize the matrix or square matrix into a eigenvalue characteristics equation, so that you can find, because every matrix follows its own characteristic equation. Suppose this is a lambda squared plus 5 lambda plus 6 is equal to 0. This is the characteristics equation. It is a lambda minus I is equal to 0. Okay. So this a should follow this. A square plus 5a plus 6 is equal to 0. So in this way you will be able to find it a square without calculating it explicitly. Okay. So that's why if you find it any matrix as an adjacency matrix, so every entry of this jth entry, kth entry of 100th power, it will be the number of walks from vertex I to vertex j of length k. You have to remember, this is important. So yeah, number of walks in what sense? Let's see. Okay, so here some proof is there. Washer circuit. Yeah, this is also called washer circuit. Okay, so if I remember, some other name is also there. Washers. Let's see. Let's see. So by induction, if you remember, if you say k is equals to 1, so by induction hypothesis, suppose the result will is true for k. So then you will prove for k plus 1, k plus 2, k plus 3, like that. Okay. So prove the result for k plus 1. What does this mean is, suppose you write is a. So if you see this particular ith row and the jth column, so I1 J1 plus I2 J2. So what does this mean is, you are equal to the number of walks. So how many walks you are doing from, suppose this is, if you are doing this power something 4, so sorry 3, so 1 2 3, so it will be 1 plus 1 plus 1, the weight will be 3 in power of a power 3. So this means this. Okay, so these are some proofs. You can check with the proof also, but I am ignoring the proof right now. So how would sir have proved? Sir just proved by induction hypothesis of how the result is true for k. So to prove the result for k plus 1, you have to prove this like this. Okay, strong connectivity of directed graphs. So connectivity, what does this mean? So connectivity, if you say, that will be characterized by the weights of the directed graph. So if let k a be a n cross n adjacency matrix, so we called a or the associated graph. So you remember, for undirected graph we call it as asymmetric. For corrected graph, for directed graph, it may be symmetric or it's not be symmetric. Why it is symmetric for corrected graph? Symmetric means A transpose is equals to A. Okay, so it should follow along the diagonal. So this you remember. Okay, now we went here. Yeah, so we are talking about directed graph here. Okay, so we call A or the associated graph G strongly connected if and only if this summation of A power K has every entry non-zero. Oh, that's great. So if you sum it A power K from K is equals to 0 to n minus 1, the entry will be non-zero. So let's see. So if we normalize the adjacency matrix, how will we normalize? Normalizing by row. Okay. So if you see this by eigenvalue or eigenvectors, so square matrix n cross n, A is an adjacency matrix, P is a normalized adjacency matrix. So if you normalize with entries of 0, 1, 0, 1, something like that. So every entry will be 0, 0 to 1. So that's why I think probabilistic will be there. Let's see. Yeah, so if you normalize it, so every entry will be between 0 to 1. That's why it is named as a probability transition matrix. Okay, this is probability transition matrix, and this all will be n cross n. So you remember every time we are talking about a square matrix. Okay, this is square matrix. So directed graph, and here A is not symmetric. So yeah, here A is not symmetric, P is also not symmetric. In a directed graph, A is symmetric and P or may not be symmetric because anyway P is dependent on A because P is a normalized version of A. But how you are not making sure that it is symmetric in case of P, that we can prove, because every entry can be same in case of A transpose to A, but in normalized case, it doesn't make sure that P transpose P. So it can be or it cannot be. So we are talking about directed graph here. Okay. So you remember this. What is the difference between this? This is important. Okay. So yeah. Uh, Eigenvalue, eigenvector decomposition. So why we are talking about eigenvalue, eigenvector decomposition? Because for square matrix we can do eigenvalue, eigenvector decomposition. That is the simplest version of C a matrix in a spectral decomposition. But for some of the matrices, this eigenvalue, eigenvector decomposition doesn't exist. For that matrices only we do that singular value decomposition. But for those matrices where this eigenvalue, eigenvector decomposition is there, then we only do this thing. Okay, because square matrices have this edge, have this more advantage. But you remember this difference between directed and directed graph. Now this is one of the theorem, Peron-Frobenius theorem. So what does this say? This states that A is a square. So one thing I would like to tell. So sometimes while you since you all are attending this week 11 week 11 this tutorial. So I remember I assume that you all are preparing for the exam. So how you have to prepare? So you have to prepare by not remembering everything, because when you go for exam and then try to remember everything, it is not possible. So week by week you remember the theorem name and their result. Don't try to remember the proof, it is not possible. And also you try to remember the concept, like suppose how the derivation of SVD come, how this is come, like why LU come, why QR come, and then what is the advantage of this, where it is used. So you have to see like this. But suppose these are some of the theorems. You don't have to remember every proof, because that proof may vary person to person. So you if you have time, you can try exploring how to have this type of proof. So yeah, coming back to this, if A is a square and irreducible adjacency matrix. So we will see what is the meaning of this irreducible. I think this irreducible means for any state, it is always a chance to get to the other state. So it will not for in a finite number of times. So suppose this is the graph I'm telling with respect to Markov chain. So this is a state, and it is possible to come from this state, and it is also possible to come from this state. So it is not an isolated state. Okay. So every state have in some point of time, suppose n time or k number of times, it is possible to get into that state. So that is a irreducible type of graph or Markov chain. Okay. So yeah. So if it is square and irreducible adjacency matrix, P is a normalized adjacency matrix. The largest magnitude of the eigenvalue of P is 1. The right eigenvalue of P is, suppose this is 1, 1, 1, 1. Left eigenvector, stationary distribution of page rank vector, which satisfy. So this. So what I'm trying to say. So here, since this P is a normalized adjacency matrix, that is also called probability transition matrix, PTM. This is P is a PTM. Okay. So here the largest eigenvalue will definitely be 1, because anyway the values of the entry will be 0 to entries of Pij will be 0 to 1. So for that largest eigenvalue, the right eigenvector of P is this. This is also called indicator vector. Okay, that is also 1, 1, 1, 1. Okay, for this theorem states this. Okay, but at the same time, the left eigenvector, that is, so if you remember, a lambda is equals to, so ax is equals to lambda x. Yeah. Okay, ax is equals to lambda x. So this x, what you call this x, is a left eigenvector or right eigenvector? What you call?
Right eigenvector.
Very true. So by default, we always calculate right eigenvector. Okay, but what if you call x a is equals to lambda x? Okay, so in this case, this x will be called left eigenvector. But since this multiplication should hold, so that's why you are transposing it. So in this case, this x will be called left eigenvector. So by default, every eigenvector that you are calculating, that is right eigenvector. But in case of adjacency matrix or graph calculations or graph analysis, we also calculate left eigenvector. Okay, so that left eigenvector is it's also called stationary distribution or page rank vector. Okay, you remember this fact. Okay, this right eigenvector is a normal eigenvector. Okay, for every eigenvalue. But if you calculate the uh, left eigenvector, okay, so that left eigenvector is the stationary distribution. What is the stationary distribution means? So after some point of time, if you calculate, this is the graph. Okay, after some point of time, this weights 3, 4, 5, 6. It will have the same weight, means it will converge to a one distribution, one probability transmission matrix, one vector. The one vector that is converging, it is called stationary distribution or page rank vector. This is important. Okay, so we are talking about a vector that is an eigenvector. The stationary distribution is itself an eigenvector that is the graph is converging. So why we calculate the stationary distribution? The first question is, so we are suppose we are analyzing a time series data, and that time series data you are representing in terms of a graph. Okay, so after some point of time, if you predict, suppose n is equals to 100, so time series data means suppose user prediction is there, user analysis of the movie, user recommendation of the movie is there. So if you calculate this, so you remember, you know that after some point of time, is after n is equals to infinity, or n is equals to 100, or n is equals to 1000, or this movie will converge to this. So you have some initial distribution, but after some point of time, from the help of initial distribution or some help of the probability distribution of the present graph, you are predicting that after some point of time, that this distribution, that the probability distribution will definitely converge to this from the initial ratings. Okay, that initial ratings you are making it as a PTM, probability transition matrix, from the graph. So here the stationary distribution is used. So if you know this stationary distribution, then you analyze and predict. And most of the cases, this pi really works. So if that stationary distribution exists, so here you replace this x by pi, because pi is called as stationary distribution, and replace a by p is equals to this. Yeah, one more thing. You are always do the stationary distribution when lambda is equals to 1. Okay, this is very important, because the maximum spread we are talking about, if you remember the definition of lambda and eigenvector, so what does the lambda means? So if you calculate for any distribution is represented in terms of matrix. So we always remember the distribution is represented in the matrix, or any linear transformation is represented in terms of matrix. Suppose it is represented in terms of A. So you are trying to calculate a vector, okay, a vector where the rotation can happen, or with that vector doesn't change its direction with the modification around the other x's. So that vector is called the eigenvector. Okay, so that if we also saw that in case of orthogonal matrix, that the vector is itself the column vectors. Okay, because those are orthogonal to each other. Okay, so rotation matrix is one of the main example of the eigenvector eigenvalue. So, but the spread that you're talking about, okay, that spread or the scaling factor is the eigenvalue. Okay, and the vector is called the eigenvector. So yeah, so in case of eigenvalue, when eigenvalue, the maximum spread is 1 because we are talking about the transition probability matrix, when the probability is 1. Okay, so in that case, that will be where lambda is equals to 1. So lambda is 1, and this is pi transpose. This pi transpose is a stationary distribution. And many times you will be asked to calculate pi. What is the stationary distribution for a graph? Okay, so this is the main essence of this. And this theorem states this. So one can have a solution and a proof also. But yeah, if you see this 1, 1, 1 matrix, that vector is also called indicator vector. Okay, let's see some of the example. So yeah, suppose A is adjacency matrix and P is the probability transition matrix by normalizing it. So you always remember the normalization is with respect to row, not column, because that also have some essence. If you normalize it with respect to column, that will not act as a probability transmission matrix. Then you have to calculate. Then you have to replace it by P transpose, not P. Okay, before that calculation is there, it will be wrong. Okay, this is the probability transition matrix. So pi transpose P is equals to pi transpose. Okay, so if you write this pi P tilde is equals to 1 minus P, this is equals to alpha. If you name any other matrix as a P tilde, and if you write this like this, and alpha is belonging between 0 to 1, then in this way also you can use hyperparameters. So yeah, if you don't know the hyperparameters, so in linear regression and all, we always add some of the scaling values. So we can have this 1 minus alpha, or if alpha, so alpha multiplied by this also have some essence. You can see the lecture. I also forgot, I watched it very long back. But hyperparameters are used for tuning. Like if you want to tune the particular values of the graph, so that is used. Okay, and that is also that alpha that should definitely belong between 0 to 1. Otherwise, the entries of P will be changed. Okay. So how to calculate? A is belongs A to N to N. Lambda is eigenvalues, X is the eigenvector. If it is this pair, okay, lambda Ix is equal to lambda X. So yeah, this is the inverse eigenvalue problem. And what do you think? Would you be able to calculate? Would you be able to calculate using only one equation, this pi? No. So this is one of the equation. A second equation will be increase of pi I is equals to 1. So using these two equations, because this is also a probability vector, okay? The entries of these two equations you have to calculate and find out. So using these two equations, you have to find out the entries of pi if for any p it is given, okay? And but if you don't normalize with respect to p rho, so you have to use this p transpose. So let us see with some of the example. So lambda x be given. Compute this so that Ax equals to lambda x. This is the inverse. How would you calculate it? Okay, you have okay, you have to calculate this A using this thing. How would you calculate? And you have given eigenvalues and eigenvectors. How would you calculate? So one of the ways, let us see Ax equals to lambda x. So equation 1, A11, this is equation 1. This is equation 2. Okay. Now equation 1, 2 equations in 4 unknowns. How will you calculate? So one of the thing is this is one of the matrices x1, x2. So if you split it this thing to this thing, this will be changed. Okay, so additional constraint is A is a symmetric matrix. A transpose equals to A. So this is giving one equation, this is giving two equation. And if A transpose equals to A, this will give another equation. So yeah, one of the thing, how would you calculate? Do you have any idea? How would you calculate? If the symmetric matrix is there, then you can estimate this A12 is equals to A21. Phi A is equals to solutions. Sir has not given. Phi A is equals to. But yeah, if more equations are there, sorry, less equations and more unknowns are there, in practice, how would you do? Basically, it will be the case of wide matrix, where we have infinitely many solution. In that case, you have to assume, suppose x1 is equals to x, then x2 will be, suppose, 4 minus x. So x can be anything. Okay, so this will be having infinitely many solutions. In the same way, if you try to calculate the eigenvectors also, so for one eigenvalue there exists how many eigenvectors? Infinite eigenvectors, right? But for one eigenvector there will be unique eigenvalue, if you remember. So that will be the cause, because that eigenvector, if you calculate the eigenvector for any, if you have calculated earlier also, you might remember that eigenvector have some k12. This k12 can be anything, right? So this is infinitely many eigenvectors exist for one eigenvalue. So this will follows the same logic. Okay, because anyway, if the less equations but more unknowns, there will be wide matrix, and that wide matrix thing, it will be having infinitely many solutions. But if you see the other case, and if you want to have the perfect solution, then you have to calculate using A transpose into inverse into y. This is the least norm solution. And if you remember the least square solution, this is A transpose A whole inverse A transpose y. Okay, and how you remember this thing? You remember you are writing like this: A transpose A, this is inverse into A transpose into y. Okay, least square least norm solution. Tall matrix and wide matrix. Okay, so one another term is there. What is the Knocker product? Okay, so if two matrices is there, A and B, so this Knocker product is defined as A cross B. So sometimes in some books it is star. So don't get confused. But yeah, how to calculate it is very important. So this is Mn and Pq. So this will be MP and NQ. This will be in MP and NQ. Here, this is not the matrix multiplication. You are extending the dimension. You remember, you are extending the dimension. So this Knocker product is A11B, A12B, A1 and B and AM1. So every element is multiplied with a B. So how it is? Let's see. A11B, A12B. So if you remember, it is expanding the dimension. It is not simple simple matrix multiplication. So what does this mean? A11B. So this is A11B means B11, B12, B21, B22. Okay, so this will be, every element will be multiplied with this. Okay, A11, B12, and A11, B21, A11, B22. Okay, so this is the first element. Okay, this is the first element. The same way, this is the second element, third element, fourth element, fifth element, so on. Okay, till this point. So this is defined as a Knocker product, and this is not a simple lattice multiplication. This is also called block matrix. Matrix consists inside the matrix. Okay, so it has some properties. So this will have MP NQ, NQLT. Okay, so this will have ML PT. So these proofs are there. You can see how the proofs are defined. So definitely we have to go by definition. So the first thing is A11B, A12B, A1NB, AM1B, AM2B, AMNB. Okay. C11D, C12D. This will be independent application concept simulation. Oh, okay. Yeah. So if you do this thing, so definitely this will come MLPT. The second property is ABC such that we can multiply them. Vector ABC is equal to C transpose this knocker product A into vector B. Okay. So some properties are there. What is the definition? You have to remember the definition, and then you can go without proof also. But yeah, if you see the proof, ABC belongs to M cross T. Okay, that is a simple matrix multiplication. That's why vector is written here. Okay, but it is equals to C transpose knocker product A into vector B. Why it is vector? It is written here to distinguish between this knocker product. Okay, so these are uh, some of the properties you should remember, but this is straightforward. For this proof, I think sir also did also go through the proof. But yeah, from where it is used. If I is B, if A is I, okay, this will be this. And knocker product with respect to I will be definitely easy. So in order to calculate vector of B, it will be this one. It is used for here. It is used here. Okay, so let's see some of the intuitions. So if lambda 1, lambda 2, lambda m is the eigenvalues, and this is the eigenvectors corresponding to those eigenvalues. So to compute such that these are the eigenpairs of A. So how will you compute? You again go by the definition Az is equal to lambda z, and if you keep the vector both the sides, so this is equals to by definition of this, okay, you will keep here, and this is equals to phi A is equals to suppose psi. This is psi. So you have to calculate this phi and you have to calculate this psi. Okay. So recall this is a eigenvalue, eigenvectors, and if m is less than n. So what is the case of this m is less than n? Tall matrix? No, wide matrix. It will be a case of wide matrix. Okay. So there will be n square unknowns, entries of A. X transpose, X transpose, X transpose. So it's a way to calculate X transpose into I. So you remember every entry will be multiplied with I. So it will be 0, 0, 0, 0 everywhere. But X transpose only 1, 1, 1, 1 X transpose is there. This is the block matrix. Okay. So there will be n square because here n up to n. So n square unknowns will be there. So special or linear structure of A, if this is a diagonal matrix of eigenvalues, and X is the matrix of if this have the special structure. So if this is a diagonal matrix of eigenvalues, and if X is the matrix of eigenvectors, so you have to compute this A. X is equal to this matrix X. So in that case, if for example when the A is symmetric, so you have to calculate using this. Okay, that's fine. This knocker product is used. So why the knocker product definition is defined? Because that knocker product can be used for calculating the entries of the matrix such that it is verifying the eigenvalue eigenvectors pair. So that is used for that. Now, uh, I hope this is clear. Even if it is not clear, you can watch the lectures for the proofs, because that proof I can't cover everything. But one more thing I would like to say, this knocker product properties you please remember. That is important. And how it is used. So we have to see with example. So that example will be helpful. But yeah, so if you see this constraint, that is important. So these constraints are also called structure constraints, because structure is used. Why? Because it is a block matrix. So this psi vector of n is a linear affine constraint of the entries of A. A symmetric, a skew symmetric, or Topli's matrix. These are some of the proper Topli's matrix is circular matrix where every row element is repeating in a circular fashion. Skew symmetric, you know, A transpose is equals to minus A transpose A transpose equals to A. As stochastic matrix, so you remember the every entries of A is summing to 1. Okay, so if you multiply A with the matrix of 1, 1, 1, okay, you write like A transpose, A2 transpose, so A and transpose, column form, so goes to 1, 1, 1. So this is actually what? Plus A transpose, this goes to 1, first entry, second entry, third entry. So this is actually the probability constraint, that is also called stochastic constraint. Okay, you remember stochastic matrix constraint. That's why indicator vector is used here. Okay. Now, till now we saw what is page rank matrix, what is the stationary distribution, what is Docker product, and also what is what is graph. So in directory graph, we saw the adjacency matrix is not always symmetric, but in the undirected graph it is symmetric, and from there we calculated the probability transition matrix. Okay, so the fastest construction matrix is important. Let's see that also. And yeah, we are trying to find how to calculate the entries of A using the eigenvalue eigenvector pair. Okay, so for that we introduce the Docker product, and using Docker product property, we are able to calculate some of the to some extent. So yeah, it's why this is important, because in case of AI ML applications, so you want particular linear function to be working in a particular eigenvector. So you want that particular eigenvector itself. So for that eigenvector and for particular eigenvalue, and you want that scaling also. So for that scaling, what will be the linear transformation, and in other words, what will be the A matrix for that? For that's why this is important. Okay. There will be so many applications there. Now, this term is very important. Fast mixing Markov chain. So, construction of fast mixing Markov chain on undirected graphs. So, you have undirected graph. In that case, A is a symmetric matrix. Okay, and P can be symmetric or not. Okay, so here you are having G is VE. Okay, V is the 1 2 to 8. Okay, and P suppose this is not 0 if there is edge, and P is 0 if it is not belong to edge. That's fine. Definitely, if it is not belong to any edge, then it will be 0. But all the entries of a row, P11 plus P12 plus P1 n, and here n is 6, suppose, like 8 here, it is 8 here, 8 will be 1, because that row sum will be 1. Then only you can tell that is a probability transition rate. Okay, so that adjacency matrix will be symmetric matrix, that's true. Then you have to normalize using this adjacency matrix, and probability transition matrix is P. Also, you have to make sure one more thing, that's summation of lambda. Okay, because when we calculate, that will be difficult. It should be 1. Okay, and this is also called page rank vector or stationary distribution. So this pi transpose equals to pi. This what is this written here? And if you calculate this pi transpose, you can calculate this pi. Okay, so this is pi. This will give you pi transpose. This is give. Okay, so this you can calculate using pi. Okay, that is important. Okay, let's see. This pi 0 transpose is equals to pi 1 transpose. What? So, Give me a second. So let's say that this is the case pi 0. So suppose 2 cross 2 matrix is there. So pi will be pi vector. Pi vector will be this one, okay? Suppose 0.3, 0.7. Definitely the values entries will be summing to 1. Suppose if pi 0 transpose equals to pi 1 transpose. Again 1, 2, why it is written here like this. I think the entry it is showing like the entry. So fastest mixing. Okay, it is mixing to the other values of the pi. Let's see some example. Very close to 1, slowly. 0, very fast. Okay. So yeah, one more thing is if the lambda value is close to 1, so it is showing that it is slowly converging. If it is 0, it is really converging to very fast. So what is it showing me? So these are some examples. Let's see the written things. Given pi can be constructed P such that pi, we know this, pi transpose P is equals to pi transpose. This is the eigenvector eigenvalue relation. Constraints are P is a symmetric matrix. Okay. In analytic graph symmetric matrix. Okay. And all the sum of the P is 1. That is for one row. Okay. This can be written like this. And for non-relation, Pij is equals to 0. Okay, non-relation is the edge. So we have to construct, the problem statement is we have to construct a Markov chain on a graph whenever there is an edge between the vertices. Pij is equals to 0 if it is not belongs to edge. Transition from I to j can happen. Okay, anyway, it can happen. So assume that P is a symmetric. So this is one of the constraints. We want to construct P such that for a given stationary distribution we have this thing. Okay, now again, this is the fastest missing Markov chain example. We will see how it is fastest missing Markov chain. But yeah, we have to construct such that this belongs. We have to construct P. Okay, how will you compute that P? So using the constraints and this relation, we have to find the equation and then we have to construct. So this is eigenvector eigenvalue relationship, and this is the affine or structure constraints. This is symmetric through undirected graph. This is for probability transition matrix, and this is for not belonging to particular edge. So, and this is also if it is should be greater than or equal to 0, positivity constraint. So if there exists infinitely many solutions to this problem, this means that there are infinitely many Markov chains which converge to same distribution. Which one to select? So definitely here, as I told you, if you calculate the eigenvector, so there will be so many solutions. Okay, you can see one of the example, you can calculate first. But what if you have to, if you want to have one particular stationary distribution? Okay, because these constraints are there. So which one to select? So we have to select the fastest converging Markov chain. Okay, so that is important. How can we select the fastest converging Markov chain? So if there exists many solutions to this problem, then this means there will be having so many infinitely many Markov chains which converge to same distribution, that is pi transpose. Okay, but which one to select? That is our ambition. So which one to select? The fastest converging Markov chain. So recall the power iteration. So if you remember the power iteration, the rate of convergence is linear. I think in week 9 it is there, power iteration. The rate of convergence should be linear. In that case, there was something last week only. The yeah, we told that I forgot that convergence. We can go also. That's fine. Yeah, this is a power iteration method. So we saw that every iteration the distance reduces by roughly lambda 2 by lambda 1. So also we saw that linear convergence is linear because every iteration the matrix vector multiplication this is requiring 2m square m floor. But what we saw basically, we wanted dominant eigenvector of because that linearly independent eigenvectors will be the case of symmetric matrix. So yeah, so if you have the linear independent eigenvectors in case of symmetric matrix, that is sure. And if you have this v1, v2, vm, and this is the corresponding eigenvalues, suppose this is in decreasing order, the power method says that if q not equal to 0, be any vector in R power n, lambda 1 is the dominant eigenvalue, v is the dominant eigenvector. So if you construct like this, so every step is decreasing by this power, lambda 2 by lambda 1, so on to lambda n by lambda 1. So this power is there. And so each iteration the distance reduces by this particular thing. So we say this it is converging linearly and it is requiring 2m square into n power iterations. This was a power iteration method that is used here. And we also saw the sensitivity analysis in the previous class. Normal equation. This is for PSD matrix. Okay. Previous one is not saved. Shit. Not saved. 1 second. The heavy rain. So one more biggest advantage that you have is you all as is able to access the notes written by sir. So you can just uh, open the video and listen the lecture at any point, and you can also see the notes as well. So you get coded with respect to notes. That I also faced the biggest advantage. So that's great. So if you have so many solutions, that which one to select? So fastest converging market rate you have to select. So if you remember the recall method, the rate of convergence because of the distance decreases by lambda 2 by lambda 1 every iteration to lambda and to lambda 1. So this is linear. This linear if it is converging to some finite number. So how fast this Markov chain converges to its stationary distribution lambda pi power 3 is determined by lambda 2p, the magnitude of the second largest eigenvalue. So this is one of the proof. So it is determined by the second largest eigenvalue, not the first largest. So this will be creating a optimization problem. So you have to minimize this second largest eigenvalue of the p such that pi transpose p is equals to p transpose equals to p, and pij is equals to 0 for not belong to h. and this is for stochastic, and this is for every entry of the P is greater than or equal to 0. Okay, how will you minimize it? Okay, so identity is the dominant eigenvalue of P, and 1 is the dominant eigenvalue of P, as we know, because this is the probability transition matrix, and this identity vector is the corresponding eigenvector. Okay, so how can you write this lambda 2p? So you can write using this dominant eigenvalue P minus, this is one of the formula, you can see, you can check. So this lambda 2p is, you can write like this, okay? So putting the value of lambda 2p here in this equation, this is magnitude of p minus 1 minus n, indicator, and 2. This is a convex optimization problem. You can use CVXPY. I used it personally in Python, that you can solve, okay, by keeping this constraints and by keeping this. And every norm is actually a quadratic function, so that you can minimize. That is not an issue at all. Okay, I hope this is clear, and if it is not clear, just let me know. So we will go directly to the questions. And this week, if you see logically also, there are some proofs, but you have to remember some of some of the things to some extent. So we saw what is eigenvalue, eigenvector, and then we see what is application in graph and vectors. So we saw what is the page rank vector, stationary distribution, and then after calculating the values in undirected graph, what is the fastest mixed Markov chain? Okay, so fastest missing Markov chain, how it will be determined? The Markov chain that has having the fastest mixing Markov eigenvector. So in that, if you want to calculate that, you have to find it using this particular optimization. Okay, NPTEL assignments. So let us solve these problems. If you want to have some break, you can have. So if you have any issues, if you have any want to talk anything, just let me know. So I think Ananta, Lakshmi, Ravi, I don't know, but yeah, Lakana have watched all the lectures. So, and even if you have not watched the lectures, you please watch the lectures and then go, because you have enough time right now also. But what is the date of exam? So anyone?
It's 19 or 26 date, not a fixed, madam.
Okay.
28.
28. Okay, so see, you have enough time, because even if you take 2 days for 1 week, because that will not require more than 2 days. So 2 days for 1 week, then you can definitely do all the weeks. And the questions, so as Lakshmi told, in week 7 or week 8, there are some programming questions. So is there any confirmation that they will give programming questions? They'll not give programming questions in the exam? Like, what if they give it exam? Did you ask them? NPTEL team or anyone? Because if they gave some programming questions, that will not be very easy, because you can't do the programming there. But yeah, I think that they'll not give programming questions. That the questions will be definitely the MCQ questions, like the previous year, or the present year. So if you do the previous year and present year, you can score definitely 80%. That's fine. So in this case, find the diameter of the undirected graph represented by the falling adjacency matrix, where one denotes the edge between the two nodes. Diameter means largest magnitude between two edges.
One, madam.
Okay, one. Anyone else? Answer is C. So from the above graph figure, it is clear that one of the farthest nodes are 1 and 5. You have to make this graph. So since this 1 is there, you have to find the maximum values, right? So 1, 2, 3, 4. How will you do? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So 7 nodes are there, okay? So 1 to 1, there's no 0, it is there. But 1, 2. So it is 2. This is 1. Let me write it different color. So this is 1. And if you go to 3, okay, 3, 3, 1 to 3, there is not a direct thing, okay? But 1 to 6, 7 is there. 1, 0, 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5, 6. So 1 to 2, it is 1 there, and 1 to 7. So 1 to 7. Okay. Let us find from 2. 2 to 1. 2 to 1 is there. Since it is a undirected graph, that's why it is 1 here. You cannot keep the direction. 2 to 3. Because 1, 2, 3. 2 to 3. This is 1. Okay. 2 to nothing else is there. So 2 has only 1. 1 or 1. This is or this is. Now 3. So 3 to 1, it is 0 only. 3 to 1. So 3 to 1, how will you 3 to 2, sorry, 3 to 2. So this is a, so you remember, this will follow because this is a undirected graph. So this is following this one. So 3 to 2 already there, and 3 to 1, 2, 3, 4. 4, 1. 3 to 0, nothing else. Now 4 to 3, definitely it is 1 there. 4 to, this is 4. 4 to 5, 1, 2, 3, 4, 5. 5. Now let's keep this 5 as, suppose somewhere 5. 5, 6 is also there. And 4 to 6. So 4 to have, it has 2. 4 to 6, 1. Okay. Now suppose we have to write like this. 2, 3, 1, 2, 3, 4, 5, 6, 7. Ma'am, any two vertices are almost 3 length apart. So we have to find the maximum difference. By making the graph only we diameter. Yeah. That's true. So any two vertices here are at most 3 length. Very true, yeah. So at most here, like this only we have to make, and we have to see any two matrices are at most because it is the diameter. So the answer is C. In your exam, the adjacency matrix will be changed and you have to find it. I think that will be clear. Okay. This is our short test. This is a maximum. This is a typing mistake is there. Okay. Second question is undirected graph represented by the adjacency matrix in question 1 is strongly connected graph? So what was the definition for strongly connected graph, if you remember?
Option C.
Only directed graph can
Only
be.
directed graph is
Okay.
connected.
What was the definition for strongly connected graph?
Option B, no. Every vertex is connected to every other vertex.
Every vertex
There's
is?
a path from every connected to every other vertex.
There is a path.
There's a path.
Yes.
Every vertex.
Every vertices are reachable. So according to you, what should be the answer? Yeah, it is connected properly, right? It is, yes. It should be yes. So directed graph is strongly connected. Okay, so can only be corrected. So this is one of the intuition. They do not possess any notion of being strongly connected since edges are bidirectional. So this is corrected one because this is falling from this definition. This is a corrected one. I think in some of the way it should be written what is the definition for strongly connected graph. If we have forgotten.
Strongly connected is directly
So you are telling that strongly connected will be only defined for a
only for
directed.
direct
Oh,
direct graph.
okay. So the first step is only like false here. Somewhere it should be written. So this is falling from the definition. That is fine. This is not logical. So yeah. So you remember that the undirected graph cannot be strongly connected. Okay. What will the order of the adjacency matrix for a graph having p nodes? Yeah, we just saw, right?
P cross P.
P by P.
Yeah, very true. This should be p by p only. The matrix square matrix with each row and column corresponding to node in graph. And yeah, we have to calculate the knocker product. So see, this is the easiest week. By seeing the contents of the week, I also saw when I was seeing it is tough, what is fastest, basic Markov change, stationary distribution and all. But if you see, this is the easiest one. So if you remember, this is 2 cross 2, this is 2 cross 2,
D1.
4 cross 4. D. Okay.
Yes, D.
Is everyone following D?
Yes, madam. D.
Okay. Because every element will be multiplied by this. 1, 0, 5, 6, 7, 2, 0, 5, 6, 7, 3, 0, 5, 6, 7, 4, 0, 5, 6, 7. I think this is 0, this is 5, this is 6, 7. Oh, this is, let's see, this is 0, 10, 12, 14. Okay, very true. This is D only. But this is also same, this is also same, this is, okay, we have now till this one. Let's see. 0, 15,
0.
18, 21, 0,
Fourth entry
20.
is 0 there.
Okay. Okay, so answer is D only. So this is the way like we can. Okay, now, oh no, so sorry. Shit. So the singular values for the matrix A are sigma 1, sigma 2, sigma 3. What will the singular values for the matrix 5? A5, A power 5. So what is singular matrix here?
There is to power 5. A.
Yeah, true A. Why it is A? Can anyone tell me why it is A? Simple analogy. Why it is A?
From theorem.
Yeah, Rantan. Why it is A?
From the theorem.
Which theorem? Okay, the answer is A, that is for sure. Because if you do the singular value decomposition is also straightforward. But even if you do this eigenvalue decomposition, so if you have found A power 5 is what? Power 5 P inverse. So you are only modifying this particular thing in A power 5. Okay, so the lambda values for A power 5 will definitely be by A power 5. Similarly, that the same analogy follows for singular value decomposition. But here you can see the singular value. See, singular value decomposition. Also, this will be same for if it is square. This will be same for this one. V is a vector of the eigenvalue, eigenvectors. Okay, I think, yeah, this is a big question. Let us solve this. Okay, let us find the entries of, let us not see the options, let us find the entries of A transpose. Take your time, just tell me in the chat box. So consider the following graph. If A denotes the 4x4 probability transition matrix, so then what are the entries of A transpose? Weights are not there. So the example is also there. The directed graph with weights is not given, but how can you find it? A directed graph with 4 vectors and 8 edges. Each vector denotes a web page and an edge between the link between two web pages. So this is one of the examples for web search. So each vector, there are suppose 10 web pages. And what is the relation between the previous web page that you visited? Suppose you want to see what the cat eats. Suppose you go with one web page and then you go to the second web page and then you go to third web page. So in that, it follows a particular relation so that we can, the number of web pages can be written in the form of vertices and the relation between the web pages can be represented as form of the widths. Okay. So yeah, here no weights are there. How can you calculate? So there's a W matter. Each outgoing edge from the vertex is divided total number of the outgoing edges from that vertex. Okay, just calculating like this. Each outgoing edge from a vertex is divided by the total number of outgoing edges from that vector vertex. So it will be 1, 2, 3, 4, 1, 2, 3, 4. 1 to 1 is definitely 0. 1 to 2. 1 to 2. How many outgoing from 1? 5%. Let me charge it. So answer is A only. So 1 to 2, how it is 1 by 3. So let's see how it is 1 by 3. Okay, I think this is as good.
First, we have to, after doing that, we have to take the transpose.
Yeah, okay, so sorry. So then it will be 1, right?
Yeah.
Okay.
Yes, madam.
So 1 to 3. 1 to 3 is 0. Now 1 to 4. Again it is 0. So 2 to 1. 2 to 1. How many outgoing? 1 by 2?
Second row is 1 by 3, 0, 1 by 3,
1
1
by
by
3,
3.
0. 1 by 3.
1 by 3, 1 by 3, 1 by 3.
Okay. So you are telling
Third row is 1 by 2, 0, 0, 1 by 2. 1 by 2, 0, 0, 1 by 2.
okay.
Fourth row is 1 by 2, 1 by 2, 0, 0.
Okay. So you are telling 2 to 1. 2
It's
to
transpose.
1. How many outgoing vectors are there? 1, 2, and 3. So 1 by 3. Okay, that's good. Okay, so how to solve this
And
type of problem also you
it's
have to see. The number of outgoing divide by total number of outgoings. Okay. So outgoing is important here. Outgoing. So this type of question I also don't know. This is also good question. So let us solve this. Consider the graph in question 6. And if V0 denotes this initial importance of each web page, if V1 denotes the importance of each web page after one click, then what is V1? Okay, so if you remember one pi 0, pi 0 p is equals to pi 1. Okay, so you have to multiply this p matrix as pi 0. 0.25, 0.25, 0.25, 0.25 with P, which will give you this will give you V1. And what is a P for in this case? I think this is only A transpose will be P here. Yeah, same here. It is written V1 is equals to A transpose V0. Yeah, same here. So transpose only. Using this equation only we have to calculate. Because the importance is so this V1, V2, sorry, P of pi 1, pi 2, pi and all the importance vectors. So yeah, if you calculate this P from here, this is the adjacency matrix. This is adjacency matrix. So we can calculate P here also. 0, 0. Here 1 by 3. Already it is 1 by, this is P only. And now multiplying with 1 by 4. This is 1 by 4, 1 by 4.
Can you repeat the question properly?
Huh? Yeah.
Can you please show the question properly? It's not really.
Can you repeat?
Can you display the question?
Yeah, which question? 7th question you are saying? Okay.
Yeah, the one we currently.
Okay, what I'm trying to calculate, this V1, using this particular equation. So this P is what? Normalized form of the adjacency matrix.
Okay, I just need to read the question. I mean, you're scrolling too fast for me.
Which question? 7th question.
Yes, please.
Okay. Consider the graph shown in question number 6. If V0 denotes the initial importance of each web page, that is the vertex. Okay. And if V1 denotes the R power belongs to R power 4, denotes the importance of each web page after one click, then what is V1? So if you remember this particular thing, the importance was given as
Here, take P as A or A transpose? As A only, no?
A, yeah, A only. We have to keep this A. P is A. P is A, but only the normalized form. That's why I'm calculating here. This will be, let's calculate this. This will be 1 cross 4, 4 cross 4. This will be 1 cross 4, right? So this is lambda transpose. So again, transpose will be 4 cross 1. Okay, this is by transpose. So yeah, so this is 1 by 4. Okay, this is, sorry, no, this will not be 1 by 4. This will be this one. You have to calculate. Can anyone calculate? This one.
0.625, 0.375, 0.75, 0.208.
0.375, 0.5.
0.7.
Last one is 0.7.
0.208.
Okay, let's see. 0.208. Last one is
0.625. 0.208.
Second one is 0.20. Last one is 0.20, right?
No, madam. First one 0.625,
Yeah.
second one 0.375,
Uh,
third one 0.75,
0.75.
last one
20.
last one 0.208.
20. Okay, so this is a vector.
Yeah.
So if you verify, so we are not getting the value. 0.625 we are not getting here. So everyone is getting this 0.625 as a first entry. Ravi?
Actually, will
My mistake. So I think there will be some on my side. Okay. So answer should verify this one, be 0.333. You can verify, and even there are some mistakes.
1 by 3, 3 by 8, 12, and 5 by 24.
So you are getting as a 1/3.
Value. Yeah.
Okay, then fine. So answer
1
is
by 3, 1 by 8, 1 by 12,
1/3, then
3 by 8,
3/8,
1 by 12,
1/12,
5 by 24.
5/12. So yeah, Lakshmi got the correct answer. So this is the answer. So yeah, using this formula, like because with the same type of questions will repeat. So using this formula, you can calculate the importance. Okay. Then you have to calculate V2. How it will be? V2 will be V1 transpose P is equals to V2. This will be V2 transpose. Then you have to calculate V2. How will you calculate? The same way. No, it is A2 square transpose. Mhm. So you can see here, but was it like this? So importance, while calculating the importance, power of A is also important. Important. Was it before knocker product or it was after knocker product? By calculating the importance. This is fastest mixing Markov chain. Okay, so the intuition of the proof, if you want how we are calculating the importance, I'll check and let you know. But somewhere in the class, sorry, in this, yeah, but we are not doing this square, right? That's what my doubt was. Uh, for calculating the importance of 1 from 0 is this one, from 2 to this one, because, but we are not doing the power of it, right? But at some point of time, it will converge to 1 pi. But initially, the importance is this one. then pi 1, then this one, then pi 2. But it is not power. So I think we have to calculate the power also. We should not calculate the power. Or what should be the correct formula? I have to check. Because here in the solution it is written power. Why it is written power? Okay. Oh, so sorry. This is 0. Shit. This is written 0, but it is V2 is equals to A transpose V1, which is equals to A square transpose V0. Same only, right? But we don't need to calculate the power. Same way we can calculate is using V1. Okay, but if you don't have V1, we have V0 because we are referring to V0, then we have to do like this square. Exponentially it is increasing. Okay, that's why I was checking. Okay. So I hope this is clear because we calculated for the previous question. Same way you can calculate. All of you got the correct answer. Lakshmi got the correct answer. All of you also got. So that's fine. Sorry. Okay, so I think this is clear. This should be clear. There will be definitely one question from this particular part. Importance. Yeah. So it comes to the question 6. After infinitely many clicks, which web page will be the highest rank web page? Any idea how will you calculate the highest ranked web page? Any thinking?
It will be the web page which has the highest number of incoming edges, also multiplied by the weight of that incoming edge.
Can't you relate with respect to eigenvalue? But which web page or vertex will be the highest ranked web page? If you remember last part, can you repeat what is your answer, Lakshmi?
I am just guessing that it is the node into which the maximum number of which has the maximum
Number of
number of
edges.
incoming edges, but also the weight multiplied by the weight of those incoming edges.
Okay. Any other guesses? Ravi?
Not only number of edges, maybe their probabilities also is to be taken into account.
Yeah. Lakshmi also interpreted the same way because she told the weight. Weight will be directly associated with the probability. Everything we are calculating with the weight.
Yes, ma'am.
Yeah. Let's see the answer. I also guess. I am guessing with respect to some eigenvalue. Let's see. Maximum value in V1 V2. So V is actually as this is a stationary distribution, okay? If you start initially from this, so if n tends to infinity, what is the distribution that is giving you? Because as we know, this is pi 0 transpose p is equals to pi 1. Pi 1 transpose p is equals to pi 2. Similarly, if it goes on, and if you want some stationary distribution pi, that is giving you either this transpose or this transpose. So p power n transpose pi 0, okay? Limit n tends to infinity. Similar way, this is written like this. So instead of solving this equation, one can look at the index of the maximum value in V1 and V2. We will find that the importance of second index keeps increasing. Hence, after infinite round, the second web page of vertex is the most important. Okay, so we can look at the index of the maximum value. Okay, index. So if we once we calculate V1, so this V1 is actually this is V1, okay? This is V1. Huh? So after V1, using V1 we calculated. Let's write this V1. Let's write this V0. This V0 is 1 by 4, 1 by 4, 1 by 4, 1 by 4. Because you also have to follow like this. V1 is 1 by 3, 3 by 8, 1 by 12, and 5 by 24. Okay. So we have to note the index 0, 1, 2, 3. Let's see which index is continuously increasing. So their import, because this is the importance vector. So importance will be given by importance vector only, okay? So that's what is related to this importance vector because that is causing the stationary distribution. Okay, so this is V1, Z0, V1. And what is V2? So V2 is calculated as, answer is D. So yeah, this is 0.436. Which one is increasing continuously? That will be the, similarly, if you need to calculate V3 also, so you have to check which particular node is increasing continuously. Because anyway, this is one node, two node, three node, four node. The second node, because as they are saying in the solution. So answer should be B. Second node is increasing. So second node is increasing. I think this is clear. We will find the importance of the second index keeps increasing as after infinite rounds. The second web page or what is most important. So even if you calculate pi, okay, because some calculating pi will be again difficult since you have already calculated v0, v1, v2. So you can see, but even if you can calculate directly pi, and using pi also the maximum value in the pi will be giving you the most important uh, vertex. Okay, so I think this is question number 9. Question number, this is a analogy question. So this type of question can be repeated. Definitely it will be repeated. So you should be able to solve. So I hope that you will be able to find the graph. From using the graph, you will be able to find the matrix, and then matrix using adjacency matrix, and then Docker product, and then some conceptual problems. So I think we have no 10. Okay, this is question number 10. The maximum eigenvalue the page rank formulation is. So what is page rank formulation? The stationary distribution formulation. This one. Pi transpose P is equals to pi transpose. Yeah, definitely. In that page rank formulation, you will keep it 1, right? I told you. So answer should be 1. Okay, answer is 1 only. This means that Vi is an eigenvector with variance. Okay, whatever it is. So in page rank formulation, this is page rank means calculating the page rank vector, or the same name is stationary vector. So the page rank calculation is giving you this particular thing. I hope this is clear. So last week is actually, let's go to the last week content itself because we have some time. So you have completed all the weeks. So you have completed all the 11 weeks. So I think 90%. And in fact, in last week, I have given so many NPTEL exams. So okay, the last week content is not visible here. So I have given exams. So uh, there will be almost negligible questions on the last week, but still you should not. So it is week 1 is sister sparse, underdetermined solution, least norm solution, sparse solution. I think this is not following this. Low rank approximation. This is already covered. Okay, I don't know what should be the last week. So I hope you will be getting the certificate for this course. So 25% of the average best 8 assignments of the 12 assignments. Okay. So okay, thank you so much for joining the session. since we have covered all the things in this week, so I think we can leave the class. And if you have doubt, you can stay here. You can ask. I'm here. One more request is there. If any feedback comes, try to give your honest feedback, whatever it is, negative, positive, whatever it is. We're also not perfect. So, but yeah, try to give that. Spare your 2-3 minutes time and try to give. Okay. So if you have any doubt, you can stay here. Otherwise, you can leave the class. Because anyway, we have covered the 11th week content. And one more thing, if you want to ask any doubt, you can mail me in this one. We can have some questionnaires in that extra week that we are having. That will be only 1 hour. So
Actually, we asked one question in the discussion forum, madam. What will be the term and examination pattern? Is it MCQ or
okay. Actually,
descriptive
I
like
would like
that?
to confirm this. Yeah. So we are not part of the NPTEL organizing team. We are assigned as an extra helping tutor to help you to solve some of the numerical problems or some of the understanding the concept or revising the things. Because anyway, these things are taught by sir. But if you say, I'll definitely ask them for on my behalf. What is a scene? What type of question they'll ask, because that will be easy for us to prepare better for you also, right?
Yes, ma'am.
Yeah. Thank you so much.
Yeah, how you are solving previous year question assignment questions now in this switch? Like that, we want to know what is the previous year term and exam question paper like.
Okay. I'll check into it. Yeah, sure.
Yes, madam. Thank you,
Yeah,
madam.
thank you.
Thank you, ma'am.
Thank you so much. Thank you so much.